Thank you very much, Professor Chu, and the distinguished member of the organizing committee. Good morning, ladies and gentlemen. I'm Tamaki Ura from the Kyushu Institute of Technology. It is my great pleasure to be invited as a keynote speaker of the Oceans MTS IEEE Taipei conference. And as Rone said, that this is the fifth ocean conference which were held in Asian countries. 2 times at Kobe, Singapore, Yosu in Korea, and now in Taiwan. I'm very happy because this successful series of oceans conference in Asia mean that we have a strong network in East Asian countries. One of the important objectives of organizing this kind of international conference is to enhance international and domestic network of researchers. Now I'm sure Ocean Taipei, which has just started, will be successful based on such kind of networks we have constructed. Last year, I resigned the University of Tokyo and moved to Kyushu by getting the position of the director of a Center for Socio-Robotic Synthesis at the Kyushu Institute of Technology. It means that I moved to the West and I approached the Asian continent. And in these 3 decades, I developed tens of autonomous underwater vehicles and operated them in the ocean. I love to talk about these stories, but today I'd like to talk about a little bit different topics. That's a governmental issue, which is a new Japanese national program. I am not familiar with talking about governmental program, but I'd like to introduce you a new program under the title of New Program for Enhancement of Development of Marine Mineral Resources. Japanese Council for Science and Technology Policy is about to start the strategic innovation programs from this month's 5-year program. And the budget is about $300 million per year. That's a very big program. And it consists of 3 topics: energy. The second one is infrastructure technologies for the next generation and local resources. And it includes, for example, in energy, combustion technology, power electronics, innovative structure materials, energy carrier, and technology for marine resource investigation. And in the second group, automatic car navigation system, maintenance, update, and management technologies for infrastructure, and reinforcement of resilience for disaster prevention and reduction. And in the third group, creation technology for agriculture, forestry, and fishery. And the last one is innovative design and production engineering. So that our research is in the 5th topics, and that's the next generation technologies for marine resource investigation. But our program title is, correctly speaking, Innovative Technology for Survey of Ocean Resources. And the target resources are hydrothermal deposit, cobalt-rich manganese crust, and rare earth elements in deep sea mud. And these are pictures of these, let's say, resources. And these resources has copper, zinc, gold, silver, manganese, nickel, cobalt, platinum, and heavy rare earth elements. And I suppose ladies are very interested in gold. So, and the innovative technology for survey of ocean resources is a little bit technology sense. So that's I nicknamed the title of this program. It's Jipangu in the Ocean program. I would like to talk about what Jipangu is. Gold, and you know, Marco Polo in 13th centuries, he came to Asia, and he wrote the travels of Marco Polo. This is a footprint of Marco Polo. He walked more than 15,000 kilometers in 20 years. And he wrote, in his book, he wrote, Japan was introduced to Europe by Marco Polo as Jipang, which produces huge amount of gold. Okay? So this is a symbol of our country. This is a golden temple in Kyoto. So that at present, the production of gold is not so much in Japan at present. But in ancient time, our country is a golden country. So that's the meaning of Japan in the Ocean program. Okay? The program leader is Dr. Tetsuro Urabe. He is Professor Emeritus of the University of Tokyo. His age is same as me. And he is also the member of the Commission on the Limits of the Continental Shelf of United Nations. And he is very responsible for definition of continental shelf. And I'm the sub-leader, so I'm responsible in technical terms. And there are many players. That's a National Institute, Japan Agency for Marine Earth Science and Technology, JAMSTEC, National Institute of Advanced Industrial Science and Technology, IST, National Maritime Research Institute, Port and Airport Research Institute, National Institute of Information and Communication Technology, National Institute for Environmental Studies, and industries should do for this Japan in the Ocean program. And the program is divided into three topics. The first one is understanding of geological feature of marine resources, which should be carried out at JAMSTEC and IST. This is a scientific program. And the second one is the development of new technologies for their survey. This is an engineering program. JAMSTEC, National Maritime Research Institute, PARI, NICT, and the industries are responsible for this program. And the third one is an environment program, the development of necessary technologies for survey of ecosystem in the deep sea. JAMSTEC and NIES are responsible for this issue. So this is let's say, caricature, a picture of the total program. And in terms of the first issue, deep sea drilling vessel GQ will be used in order to know what the under materials on the seafloor and under the seafloor is. And also they use remotely operated ROVs in order to survey the mineral resources. And the engineers should develop new technologies for seafloor survey. We would like to, we are going to construct, say, big team of autonomous underwater vehicles and remotely operated vehicle. And the third group should develop necessary technologies for survey of ecosystem in the deep sea using observatories connected with seafloor cable network and so on. So now I would like to introduce some topics of 3 targets. And this picture shows the North Kihia hydrothermal vent field. And the knowledge about physics, geology of deep sea minerals are not so much comparing to mines in land. Before 2010, we knew that there are some hydrothermal mounds in the area of North Ihia field, but the size is estimated as size was estimated as 100 meter in horizontal size, and height is about 20 meters. But GQ did during 2010, and we found that the very huge volume of hot water and mineral deposit are existing beneath, under the seafloor. So it was just found 4 years ago, and then you know that the size we estimated before 2010 is very small comparing to the data found in 2010. And after that, 2014, this year, remotely operated vehicle of JAMSTEC found 2 new sites where with hydrothermal activities. And this is a map. Old one is located at the center of the very huge caldera, and JAMSTEC found 2 new sites. So that these large area under the seafloor, we hope there are very huge amount of hydrothermal deposit. So it means that our knowledge about deep sea mineral resources is very, very limited, very small. So that scientific research work is essential in order to find out many hydrothermal deposits in wide ocean. So that this is the first topics we should do in the Japan in the ocean program. And the second one is a technology of remotely autonomous underwater vehicle. R2D4 is one of the vehicles I constructed, and it was born June 2003, about 10 years ago. And the vehicle has many sensors in order to measure the sea floor. And this is a replay of actual motion of R2D4, which was carried out in 2005 in Myojinsho caldera. And we found a new hydrothermal activity at the central cone of this caldera. And the diameter of this caldera is about 7 kilometers. It's a very big one. So that the AUV can do something for finding the mineral hydrothermal activities in the deep sea. So, and another, let's say, operation of AUV R2D4 was done at Izena Cauldron. And this is a joint program between University of Tokyo and JOGMEC. JOGMEC is a governmental company, Japan Oil, Gas, and Minerals National Corporation. And this is a dive plan of R2D4 I designed about 6 years ago. And the vehicle successfully carried out all dives shown in this figure. So that, and here, Hakure site, just a very big let's say, hydrothermal vents area. And the jade site is here. Jade site is the first hydrothermal vent field we found in Japan. So this is a side-scan image around the Hakure site. And because this side-scan sonar image was captured by R2D4, which swims only 60 meters above from the seafloor. So you can see mounds like this way, and this is a close-up of hydrothermal vent field. And you can see many small mounds and chimneys on the seafloor. So that the AUV is a very powerful tool to find out new hydrothermal areas. And I would like to show you how effective it is. This is a bathymetry map captured by surface ship. It's a very conventional way. And the depth is about 1,600 meters. So that the bottom of the seafloor looks very flat. And this is a 10-meter contour map. And this is the results of the survey of AUV R2D4. So in the this was measured from 60 meters from the seafloor. So that's how we can see many small features of the seafloor. This is a very big advantage. From the seafloor, from the surface, we cannot see anything. So that the AUV should be operated as possible. So AUV should cover very wide area of the seafloor. So this is another image of the seafloor is in a cauldron. So that in the next, in a new program, we are going to construct a group of AUVs which can be operated from one research vessel or one small ship. And they should survey wide area in a short time because swath is very narrow when the vehicle goes near the seafloor, so that it takes very long time to cover very wide area. So that's a multiple vehicle system is essential in order to cover wide area of ocean. And the next target is on cobalt-rich manganese crust. And this is a picture of manganese cobalt-rich crust taken by a remotely operated vehicle. And so that the left-hand side bottom, you can see the cross-section of the crust. And this is another picture. And number 5 Takyo knoll is very important, and let's say knoll. We suppose that there are very huge amount of cobalt-rich crust. The depth is about 1,400 meters. And around Japan main island, there are many knolls, and the red dots indicate the knolls. But there are so many knolls, so that's and almost all knolls has not been investigated, surveyed. And also, in the right-hand side, you can see the cross-section of the cobalt-rich crust, and the about 20 centimeters thickness. It may take about 1 million years. So scientists have found that based on the element from this sample, that the speed of growth changes in 1 million years. So that's and this is a very new finding. So that the scientific research is also very important, and also survey of wide area is also very important for in technological point of view. So that in order to let's say accelerate survey, we are now developing an acoustic system which can measure the thickness of the cobalt-rich crust. And the thickness is about from 10 centimeter to 20 centimeters. So you can see this is the video image of cobalt-rich crust, and the surface is very flat. And in the bottom, you can see the data of reflection of acoustic pulse, so that we can measure the thickness of cobalt-rich crust like this way. So that based on such kind of data, we can estimate the total amount of the crust in 1 node. So this is this shows the results of the measurement of the cobalt-rich crust, and it shows that the thickness is about 10 centimeters. So that's a technology, and we are going to implement this system to a new autonomous underwater vehicle in order to accelerate the speed of measurement of the thickness of cobalt-rich crust. So, and the third target is rare earth elements in deep sea mud. In 2011, 3 years ago, Professor Kato of the University of Tokyo showed the data of rare earth element in the mud of deep sea, and he said that there are very high concentrated rare earth elements, high concentrated mud at the in the mud, and so that I would like to show you the recent results. And the professor's Kato's data is very, very impressive. So that's a Jamstack and JOGMEC did sampling of seafloor near South Torishima Island. And so that they found just 5 or 10 meters depth of deep sea floor, more than 6,000 ppm total rare earth elements are existing. And it is not a manganese nodule, it's mud. So mud is not so difficult to pump up to the surface. So that's, and we are now very, very interested in rare earth elements, but our knowledge is not so much, as I have said, in case of hydrothermal deposits. So that the basic research is also very important in order to know why and how thick these muds are existing in the deep sea. So finally, I would like to say that the gold and platinum and rare earth elements should be brought from the deep sea to the surface in 5 years or so. And then after the program, I would like to bring ingot of gold here. And I would like to show, oh, this is a gold from the seafloor. Thank you very much for your attention.